Hi everyone, and welcome to this, which is the first in our webinar series for 2016. My name is Tom Pritchard and I'm the host for today's session. I'll be introducing you shortly to our speaker, Dr. Colin Smith, and also rounding up at the end. Today's webinar has the title Delivering Better Geotechnical Designs with LimitState GEO, and it will explain how LimitState GEO can be used to improve the workflow and also influence your geotechnical designs. You'll find out a little bit about the technology behind the software and see how it's applicable to a wide range of different situations. The main section of the webinar will run for about 45 minutes until approximately 1:15 p.m. UK time, and there'll be some time for a few questions at the end, which can be posted at any time via the question functionality that's present in the webinar interface in front of you. We do try to answer as many questions as we can within the webinar, but given the amount of time available, we can't always get around to all of them. So we will, however, follow up on any unanswered questions after the webinar is finished. And if you do have some specific questions regarding the software, you're always welcome to contact us outside of the webinar via info@limitstate.com, and we'll be more than happy to answer these in detail for you. So without further delay, our speaker today is Dr. Colin Smith, who is the LimitState GEO Product Manager, and I will pass you over to him.
Thank you, Tom. As mentioned today, my aim is to give you an introduction to how LimitState GEO can be used to simply and easily model geotechnical problems. So we'll be looking at workflow with the software, how it can be used to conduct what-if type calculations, and a quick look under the hood, how it works, the technology that it uses. So to this end, I'll primarily be using the software directly to illustrate the key points, but we'll make use of a few slides at the beginning and end for an introduction and summary. As this is a short presentation, the main aim is to give you a flavor of what the software can do, so there won't be time to get into details of everything that it can do, but there is time for questions at the end. So the main part of the presentation will take roughly 30 minutes, and we'll have 10 to 15 minutes for questions at the end. So firstly, a little bit of background about LimitState. The University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. And the company was spun out from the university in 2006 with the aim of making this research available to industry with a range of innovative software products. LimitState, the company, we focus on tools for ultimate limit state analysis. So to put this in context with other currently available software, on the one hand, up on the top left of the screen, we have generally easy to use software and spreadsheets based on conventional hand calculations type methods that can handle a specific problem type. And on the other bottom right hand corner, more complicated finite element software, which can model any geometry and can model complex soil behavior. We think there's a gap between these two, and filling that is computational limit analysis or plastic analysis, which gives you the geometrical flexibility of the finite element approach, but the ease and use of and simplicity of the traditional approaches, where the only parameters you require are cohesion, friction, and unit weight. And this same approach may be used not only in geotechnics, but for example in the analysis of arch bridges or in concrete slabs. Now, by using this approach, LimitState GEO is able to determine the collapse state for any problem geometry that you can define, and it's able to model slopes, retaining walls, structural elements, and soil reinforcement, as shown by some of these examples. Similar flexibility is found in the other LimitState products. So at present, we have LimitState Ring for masonry arch analysis, LimitState GEO, and LimitState Slab for concrete slab analysis, and several more in the pipeline. And these software are used across the world by a wide range of companies, large and small. So that's a quick introduction. Let's try out the software, and we'll look at the sort of workflow, how you go from start to end in terms of solving or analyzing a particular geotechnical problem. And we'll look at the problem of a retaining wall design in the context of the widening of an embankment. So we have an embankment here that is to be widened. It has a a strength we assume of 27 degrees, friction weight of unit weight of 18, and a height of 5 meters. To widen it, we're going to put in a stem wall and backfill with a granular material, and that material is going to have a higher angle of friction. So the question might be, how wide should the foundation be, and is it going to be able to take the specified loads, which in this case are 3 different loaded areas as shown in the diagram. So if you're going to do that by hand, conventionally you might use a virtual back and assume a Rankine earth pressure distribution, but that's complicated a little bit by the fact you've got this inclined interface between the existing embankment and the new fill, and because of the varied surface loads. Perhaps more appropriate is Coulomb wedge analysis. You try different angles, but even that can get quite complicated, and you could well miss the critical failure mechanism. So how would you do it in LimitState GEO? Well, you might start with an import of a DXF drawing of the geometry. So we'll do just that and show you how that works. So I'll start up the software, or bring that up. So this is effectively what the software screen looks like. A number of buttons around here, a number of windows which we'll explain as we go along. So I will click File, Import, and import geometry, and I've got this one set up already, so that gives me a DXF file, and I get some information about what I'm importing here. I'm just going to click OK, and up comes the required geometry. Now that may include some construction lines. Just for simplicity, I'm going to clear those and see where I go from that. So initially you might have a sort of outline design, but you might not have a detailed site investigation. You might want to do a scoping study, but you might have an indication of the soil type. So the software on the left here, what we call the Materials Explorer, has some built-in standard materials, sort of conventional designation and typical strengths, and we could use those to get a feel. So let's, for example, assume in this case that we have a very stiff clay down here. You just drag and drop the materials there, and I'm just going to simplicity use firm clay everywhere else in the problem, and use concrete for our wall, such like that. We need a loading, so I'm going to put a load up here. So I've clicked on a boundary. I can define permanent, variable, and accidental loads. These correspond to the sort of Eurocode type designations. So I'm going to put a load of 10 here. So there's my load. And I could click solve there. Now what happens is that whenever you click solve, you get a diagnostic message that gives you some information about how you set the problem up. We won't look at that in much detail, but very useful in just checking that it's set up the way you intended. But we've got an error here, no support has been applied, and of course we need some boundary conditions. So I can select points on the geometry here and here on the edge. I'm going to change the boundary condition from free to fixed. So everything I click on in this main screen, its properties appear on the top right here, and I'm going to just flip those like that. Then hopefully this should now solve. And what the software does is it very rapidly hones in on the critical collapse mechanism using an upper-bound sliding block type approach that you may be familiar with from hand calculations, but instead of, a bit like Coulomb wedge, but instead of just one wedge, we've got maybe 20, 30, 40 wedges involved in this analysis, and the software will always pick out the most critical mechanism. So we get to see the mechanism, the deformation pattern, where it's deforming, and we get a solution down here, and this is what we call the adequacy and load. And essentially what that means is, in order for this failure to occur, this surface load of 10 has to be multiplied by 17.5 to cause collapse. So that's quite a wide, big margin of safety on that one. But for different problems, we'll get different solutions. So that was a quick example of just a sort of what if with general soil types. Let's work with the actual soil types defined in the problem. So I've got a pre-prepared model, this one here, which has the actual problem as defined in the PowerPoint slide. So if I click on here, I can see the properties. We have the existing fill, which had a strength of 27, unit weight of 18. The new fill has a strength of 34, unit weight of 18. And the loading up here, for example, the central load here was 45. And the side loads were 10. So, having set that all up, again, I can just click solve, and the software will rapidly identify the critical collapse mechanism in this case, animate what's happening, and tell me what I have to do to the loads to cause collapse. Now I've set the software to actually apply Eurocode partial factors, design approach 1, combination 2. We'll come back to Eurocode a little bit later. And it's telling me that actually for this system to collapse, I need to multiply the load by 0.771. That's less than 1, which essentially means this system is going to fail and the loads are too big at present. So this isn't going to stand up as it is. So it's unstable. But what we can see is that if I click this button here, this is animate the system, we can see that we're getting sliding down this interface. So actually, the strength of this granular fill, which is higher than the existing fill, we're not using all of it because we're just sliding down the weaker existing fill. So one possibility would be to put more fill in and take away more of the existing material. So I could very simply pull that back like that. Just change a little setting there, maybe put it back to there, and see what happens with the analysis. So click that again, and what that's done is it's forced more of the mechanism to stay in the new, stronger fill, and we've got an adequacy that's just above 1. So technically that now complies with the code, slightly over-designed, but it is appropriate for what we want. Now, what we can also see, if I animate that again, is that the failure includes failure underneath the base. We're getting some bearing failure and sliding together. And maybe that's causing some of the problems here. So we might say, well, I really don't want to add more fill here. I'd rather leave as much of the existing embankment as possible. What could I do down here that might help? So let's replace this material here with this stronger basal fill material. So this basal material here wasn't in the original PowerPoint, but as a deposit, I've put that in as a strength of 40 degrees and a unit weight of 20. So it's actually represented up here. I can just drag that along and drop it on there. So I've now got that fill there. The other thing I need to do is alter the interface material. So what you'll see here is a slightly different color there. We can actually apply material properties to boundaries or interfaces. So in this case, what I had applied was a granular fill wall interface material, which I'd defined myself, and said that its strength was 3/4 of the parent material, which was the granular fill. Now the material we're adjacent to is the basal fill, so I want to change that. I've already predefined that as this material here. It's got a strength of 3/4, but its parent material is now basal deposit. So I'm just going to drag and drop that on the interface, and we have that new problem. So if I solve that again we'll find the critical mechanism, and this time it doesn't want to fail. That material is now strong enough, and we just get a sliding failure, and we get quite an increase in the factor on the load that we can get away with. So that's a much better improvement. So we're busy exploring different ways of dealing with this load capacity. I'll just revert those. Now I can either change them back, but we have an undo button up here, so I click undo, and we're back to our original materials. And what we could look at is maybe the benefit of surcharge here. So just to make life easier, I put a kind of polygon here that's a bit squashed, And if I select that boundary and just pull it up a little bit, it's then basically representing adding some fill in front of the wall. And if I click solve here, I get this factor on load now of 1.86. So that berm there has quite an influence. We don't refer back to this result, which is when we change the fill under the base, but back to the 1.1. So that has improved matters. And we might say, well, that's probably pretty good. Let's get rid of this point and not bother with extra fill behind the wall. So I can just click on that point and delete it and solve again. And I've still got a decent margin there. So I have additional capacity. So I might say that's a solution I'm happy with. Obviously, we've gone through a fairly simple process here. And at the end of the process, having started with that DXF diagram, created some materials, I can get a report, click report here, and this will generate a report that is, we can either save as a PDF or as a rich text format, which you can then edit very easily with something like Word for Windows or other word processors to adapt to your own style. But it gives you a bit of background about the methods, summary of the problem, the collapse mechanism, data about the boundary objects, what materials you've used, their properties, partial factors in the system, etc. And if you wish, you can get free body diagrams of the problem, which essentially show you a sort of Coulomb wedge type analysis. The nice thing about the software is you can set it to generate a very simple mechanism. Won't be that as accurate as this one, but reduce it to 1 or 2 wedges, and if you want to check it against, say, hand calc, that is possible. So shut that down. Just look at, before we leave this problem, look at 2 other aspects. So we originally asked how wide does the base of this stem wall have to be? So we could simply say, well, what's the impact of increasing that? So we're just going to click on these 2 boundaries here. Oops. Holding the wrong key down, and I click, we have an ortho button here. That just basically means when it's set, anything I drag will only move horizontally or vertically. So I hang on to that, and I can just pull that back a bit, make that a bit longer, see what the effect on the analysis is. And that's changed the mechanism, and we've gone from one previous answer of 1.48 to 1.9 in terms of load. Factor of safety on the load that's applied on the surface. So that also has an effect. So we can play around with the parameters to see. I'll just revert that. Last thing that might be of interest is, had we done that hand calculation with a virtual back, I could draw in a virtual back here, and with a hand calculation, typically you assume that that interface is frictionless. So I'm just going to create a frictionless material. I can use this tool button, create new material. We'll call it frictionless. Give it a color, say blue. Let's make it a drain material, but we're going to basically give it 0 strength, 0 weight. Put that in. That's now appeared here as part of the materials, and I can drag and drop that onto these 2 boundaries, and that simulates a virtual back. And if I click solve, we see actually that that's quite a conservative assumption. We've now brought the adequacy below 1. It doesn't comply anymore, but that's because we've effectively made an assumption that the system is weaker than it actually is. But we can get a feel for how that would relate to a hand calculation for this problem. Okay, so that pretty well wraps up that look at how we might go from initial DXF right through to report. If I just revert back to the PowerPoint, talk a little about what-if analysis. Now, of course, we've already done a little bit of what-if in that problem that we've looked at, but we're going to have a quick look at a slope stability example. So here, I'm just taking a very simple slope example. 10 meter high slope, 20 meter along with C' to 5, phi' to 30. It's actually taken from an example from the textbook by Whitlow, and he analysed it using Bishop's simplified method of slices, got a factor on strength of 1.6. Of course, when you use method of slices, you've got to make some kind of assumption about the interslice forces. And often, if you're using software, you specify where the slip mechanism enters and exits the slope, and where the center of rotations that you should search through. With LimitState GEO software, you don't have to do that. It's based on rigorous plasticity theory. It doesn't require any of these assumptions. So we'll just have a go at opening that. So I've pre-prepared that particular problem. It's this one. So there's a slope. Again, if I click on that body, look at its properties, we've got the C' to 5, phi of 30, unit weight of 20. Just click solve. Now what we've got here is there's a setting up here which says factor load or factor strength. The previous problems we were looking at factor load mode. We were saying how much bigger, what's a factor on the load that would cause collapse. Here we're going to ask the software what factor do we have to put on the strength of the material in the slope to cause collapse. So I click solve here. It takes a little longer, runs through a number of different scenarios and quickly identifies the critical slip mechanism, which is this one, animates it, and it tells me I've got a factor on the strength of 1.63, which compares very closely to that method of slices result of 1.60 from Whitlow's analysis. Now we might ask, well, how would that be affected if we put a surcharge, a building or a vehicle up on the top of the slope? So let's say we don't get right to the crest of the slope. We put a load of, say, 5 kilonewtons per meter squared. Will that have an effect? So we can run that analysis. Again, we get there pretty quick, and what we find is that really hasn't had much effect. It's not really changed the factor, and in fact the mechanism has not involved this surface load at all, so the failure is dominated by the weight of the material here. Now we could say, well, what if this was a lot heavier? Let's up that by a factor of 10, 50. Does that make a difference? So again, we run through that analysis, and what we find is that indeed that does make a little bit of difference. We get an answer of 1.56, so it hasn't made a huge change, down from 1.63 to 1.56, and the fact we've got a load there has moved the failure surface back a bit, and that does influence things. Of course, with slope stability analysis, there's always a risk of pre-existing failure surfaces. That's very easy to model in the software. So for example, let's assume we had a pre-existing surface that, sorry, I've got this ortho button on, let's turn it off. That runs from, say, here to here. And we'll just give it we can make it curved by adding a number of segments to it. I'll keep a very simple bilinear curve in this case. And let's assume, for simplicity, I'll just put the weakest standard material on here, very soft clay, onto that interface. How does that affect the stability of the slope? So I click solve again. And what you can see this time is that the failure mechanism clearly favors sliding down that pre-existing surface. And in this particular case, the adequacy is now below 1. It's not safe. The material needs to be stronger to avoid collapse. And we have a kind of problem there that we need to stabilize. So we could change the geometry of the slope or add, say, a berm at the front. And that's very easy to do in the software, but I haven't got time to do that in this particular session. So we're going to just look at quick look at one other problem type, which is a footing problem. So here we have a very simple foundation, block of material with a load on it applied to a body of soil. This soil is, we're going to model it as an undrained problem. We've got drain and undrained properties. You can define both and then tell the software whether to do a drained or an undrained analysis. This one's going to be an undrained, underend strength of 70, unit weight of 20. What we have is a surcharge either side of the foundation here of, let me just find it, 10 kPa. And rather than specify a particular load on the foundation, we're just going to say how big does that load have to be to cause collapse. So if I click on here and look at the load that I've defined, I've actually defined it as a half. And the reason I've defined it as a half is that that foundation is actually 2 units wide. Its geometry is given down here. Starts at -1, goes to 1, so it's 2 units wide. Multiplied by the half means that I'm effectively applying 1 kilonewton per meter width of footing into the diagram. So the question we're asking the software is how big can that load go to avoid collapse? Now what I want to demonstrate here is the use of partial factors. We have what's called a scenario manager here, and it makes it very easy to apply partial factors and get a feel for their effect. So I've set 3 scenarios up here. First one is to apply no factors, all unit. Second one is design approach 1, combination 1 factors, where the applied loads, depending on whether they're favourable or unfavourable, are factored by 1.35, 1.5 or 1, but the materials aren't factored. And design approach 1, combination 2, where in essence we factor down the material properties. So we can get a comparative feel for how those work. So again, I just click solve. We're in factor load mode here, so we're just saying what is the load that causes collapse. So the software will run through 3 scenarios and give you each of those analyses on different tabs here, and the asterisk indicates the worst case, which is design approach 1, combination 2, and essentially it says we can put a load of 500 kilonewtons per meter onto that foundation before collapse. Now, this foundation is on the surface. Clearly we normally bury those, so we could look at the effect of that. So here we have a value of 500. I'll just open a file which has that model in. So while this foundation may look smaller, it is still actually has the same width of 2. I've just made the domains out here wider to accommodate the larger mechanism that occurs. Everything else is the same, so if I click solve, what we get is the benefit of this extra surcharge here, extra soil and the extra shear strength of that soil. In this case, and we get an enhanced load of 650 in this particular case. And it's very easy to look at the effect of, for example, an inclined load or an additional horizontal load. So here I'm clicking on the load. The normal load is a half. I'm going to apply a lateral load of 0.2 as well. So that's now inclined. See what effect that has. And we get a very different mechanism. And we get a reduced capacity because of that combined loading situation. So hopefully that shows you that we can very easily set the software up to analyze different scenarios, which in this case encompass different Eurocode factors. We can also set it to analyze both drained and undrained problems in one go. So what hopefully you've seen is the software is generating collapse mechanisms. These are the critical collapse mechanisms that will occur in these loading. And what I'd like to do is just go through how that works. So we're going to just jump back to the slides. Just very quickly explain how the software identifies those collapse mechanisms. So it's using a technology called discontinuity layout optimization. This is a rigorous upper bound plasticity method published in the Proceedings of the Royal Society in 2007, and it's quite easy to explain. It's not a finite element method, it follows a very different approach. Let's take a very simple example here. We have a block of soil, rigid boundaries to the base and to the left, and a load up there. What we do is we populate the domain with nodes, not with elements. So here we've got 12 nodes, and we connect every node to every other node, which in this case gives us, I think, 66 possible connections. Basically, we formulate the problem as a linear optimization problem, feed this into an optimizer, and get it to pick out rigorously the key slip lines which give the critical collapse mechanism. So this very simple problem, there are 6 slip lines which give us the critical mechanism, out of those 66. Very easy to identify using linear optimization, and the software will find those. Generally, we're using 500, 1,000, 2,000 nodes in a problem, and that's normally enough to get you within 1 or 2% of the actual result. And when the software has solved the problem, it will, having identified those slip lines, then put them together as blocks so that it can animate them, and that just helps interpretation, as you can see in this slide. How well does that work? Well, this is one example, applying it to it's the sort of foundation on a clay soil or the pyramidal punch problem, and you get within 1% of the exact solution with about 1 second with this. And you can see the fan zones identified here and here. What's very nice about this method is that it handles mathematical singularities without difficulty. So a key issue that comes up many times in collapse mechanisms is that the slip lines all meet at a point and you get these fan zones. That's quite tricky to deal with in finite elements because it's a mathematical singularity. In this approach, those are just dealt with inherently, no special programming required. You obviously would want to know how accurate this system is. Well, we've compared it against many solutions available in the literature, and we get very close matches. We put around about 100 of these on the website. You can look through the whole list and see how different problems, retaining walls to anchors to slopes, etc., how they compare. And every time the software is modified, it runs over 1,000 tests, including these, to ensure that it's still doing the right thing. There's also quite a lot of literature out there now using the software, over 30 publications in international journals and in international conferences. Again, you can download this bibliography off the website, and it lists all the papers that have been published applying the software to, say, foundations, slopes, retaining walls, seismic problems, etc. Just to wrap up, show you a few more application examples. So this method of identifying slip lines and the optimal mix, we can analyze Gaussian walls. We look at, for example, what happens if you dig a trench next to a foundation. How will that change the stability? How close can you get a bit of plant to the edge of a working platform? Stability of an anchored sheet pile wall here, and we can model water. There's a pipeline, lateral loaded pipeline on the seabed, key wall here, and complicated slope geometry with a retaining wall, 2 layers of different soil types, and the software is able to find the mechanism that runs down the kind of interface there and then dives into the stronger, deeper material under the wall, and so on. So hopefully that's given you a flavor of what the software can do. So just to conclude, hopefully you've seen it's a straightforward workflow from importing the geometry to reporting the final result. We have a very intuitive user interface, puts you in control of what you want to change, how to change it. You can solve the problem with one mouse click, and it's easy to put in partial factors. It's a very interactive software, so a lot of our customers use it to answer those what-if type questions, play around with parameters, see which ones have a big effect, which ones have a small effect on our final design, where we might need to get more accurate information about a particular parameter, so you get a better feel for the problem, and that we can solve any ultimate limit state problem type. We don't need to put any idealizations or correcting factors for non-standard geometries. Often we need to do that if we're using a sort of standard solution for a particular problem type. No need here. And no need to learn how to use many different programs. So that wraps up where I am. So we've now got a few minutes for questions. So, questions we have. Can we model reinforcement, for example, in slopes? So the answer is yes. I can show you an example of that. We'll do a very simple example. So one thing I didn't show you in the software is, as well as being able to import geometry and you can draw your own geometry, we have some quick build wizards which allow you to build standard problem types. So here I'm just going to go for slope stability. You can put in a number of parameters to the dimensions and the soil properties. We're just going to accept all the defaults. We get a fairly steep soil here. And if I solve that, we get a failure mechanism of this nature. And we're analyzing in a factor strength mode, so the strength of the soil would have to be reduced by 2.4 to cause collapse. If I want to put some reinforcement in, I can. Those get put in on boundaries, so I can draw in a line like that. I don't know, there, and put in some reinforcement. Now, we have some built-in standard ones where you can define your own. I'm going to use the standard one here. If I click on this, it says soil nail rigid. Essentially, you define some pull-out factors, moment of resistance for these materials, and so you can tune it to whatever your particular reinforcement you're using. We'll just use the built-in default. I'm just going to drag it and drop it there. So now we've effectively put a soil nail in this slope. And then I can rerun the problem and see if that has affected the collapse. So in this particular case it has. We've now changed the failure mechanism. It's got bigger. Effectively it's trying to go round the nail and avoid interacting with it. We can see the distribution of stresses in the nail here. We get a plot of axial force, or we can plot the bending moment. And we can see what it's done to the factor and safety of strength. Here it's 2.668, so it's gone up a little bit, not a huge amount, but if we could put more reinforcement in or make it longer, and we would get a further bigger gain. Okay, another question, just trying to... Got a question saying, does the software have applications for ground improvement techniques, for example, for settlement calculations? So I guess the answer is no. In terms of settlement, the software is an ultimate limit state software, so it's looking at collapse. So it doesn't do settlement calculations. If you're looking at ground improvement, I mean, you can model the effect of ground improvement, whether that's using just generally increasing the strength of material, or you're putting inclusions in that increase the strength locally, so you can easily model, for example, stone columns or such like. But again, you'll just be assessing on strength in this case rather than on settlement. Okay. Another question. Can we solve seismic problems? Yes, we can. We've got a little box here. It says seismic actions. This allows us to put in accelerations that are pseudostatic accelerations that are horizontal or vertical. So I could add, for example, a lateral acceleration of 0.2 in this case and see what that does to my slope stability. And we've still got my soil nail in there. See if that affects things. And we get a different mechanism. And the factor of strength has gone down 2.12 from 2.6, so that horizontal acceleration is encouraging the slope to fail from right to left, and we're getting that failure. And we can also ask the software how big an acceleration would cause collapse. So we can actually define the question we ask the software in quite a flexible way to give us the answer that we would like. Okay, just looking at other questions. Can we import any other drawings or files? At the moment, really, it's just DXF files that you can import. But many drawing packages you can convert to DXF. But if there is a strong demand for those sorts of facilities, we can add those to the development list. So if that's something you'd like, let us know if there's particular file types, and we can look at that. Okay. Another question. Can we model Hoyt-Brown materials? So trying to model rock masses. So Hoyt-Brown materials generally we've got a curved yield surface. Software is primarily set up to model materials with more Coulomb and linear surfaces. So if we're modeling a drain material, we're basically defining a cohesion intercept and an angle of friction. What we can do in the software, however, is model a problem where we have more than one material. So just thinking of a suitable example here that I can pick. Let's pick the gravity wall. So I can put a sand soil behind here. Now that has an angle of friction of 30 degrees, zero cohesion. What I can do is I can also put in other materials. I'm just going to duplicate that material. So I've made a copy of it, but I'm going to edit it, give it a slightly higher cohesion intercept and a lower friction angle. I'm going to give it a different color. And I can drag and drop it. You see when I drag and drop, I get a choice to add or replace. Normally I've replaced, but I can get a combined material, which comes up in this checkerboard pan. And that means that I get the combination of the two yield surfaces. And actually, if I put in 3 or 4 materials, I can actually pretty well replicate a curved yield surface with a series of straight lines. And the soil will always take the weakest material that I've defined. So that way I can model sort of curved surfaces, yield surfaces, such as Hoyt-Brown, or in fact, most real soils technically don't have a more Coulomb surface. They have a slightly curved yield surface. So there is the scope to look at that. Okay. We're pretty well coming close to being out of time there, so I'm going to wrap up there. So thank you very much for listening in. I hope you found that useful and interesting, and I'll pass back to my colleague Tom Pritchard to wrap up the seminar.
Thanks, Colin, and thanks everybody for listening. We're now quite near to the end of the webinar. We do hope you found it informative. For people who are current users of the software, we do hope that you learned something new about it, and maybe there's something you didn't already know about it. And if the webinar has prompted any questions, then as we mentioned at the beginning, please do get in touch via info@LimitState.com and we'll be happy to help. For those of you who aren't current users of LimitState GEO, we'll just be in touch over the next few days, get some feedback from you to find out whether you have any further questions and see whether you think LimitState GEO may be useful to you. Everyone may also be interested to know that we have a number of forthcoming webinars that we're planning for this year, covering all the LimitState product range, so LimitState GEO as well as LimitState Slab, our concrete slab yield line software, and also LimitState Ring, our masonry arch analysis software. These will all focus on particular problem types and applications, so please do look out for those and for the event notifications that we'll be sending out by email and posting on our website at www.limitState.com/events. So finally, thank you again for taking the time to join us today, and we do hope to see you all again for one of the future sessions. Thank you.